Okay, so we talked about the basics of transduction, right? What we mean by converting energy from one domain to another. We talked about some of the terminology that is used. In case of sensing or actuation, this is where we get involved and we want to get information from the environment through sensing, or we want to act onto the environment through actuation. And usually the command that we send to actuators, or the information that we receive from the sensors, we'd like them to be in electrical domain. So usually one side is electrical, the other side could be directly the environment, or it could go through a couple of transductions before you have an electrical signal. So what we're going to do in the next few lectures is that we're going to talk about the transduction mechanisms that are important to us at microscales. A lot of these also have applications at larger scales. And today we start with the probably the most familiar one, piezo-resistive sensing or transduction. And then we talk about piezoelectric, thermal, and electrostatic transduction as some of the more common transduction mechanisms at microscales, and also talk about a few other ones that are not as common but have their own place in the industry and in the field. So what is piezo-resistive sensing? Well, as the name suggests, it's a response that changes the resistance or the resistivity in some cases. Piezo is from a Greek word meaning stress or pressure, and piezo-resistive means the transduction mechanism where a mechanical stress or strain changes the resistance or resistivity. Note that these two are different. Resistance is what you measure with a multimeter, with a voltmeter, with an ohm meter. Resistivity is a property of the material. So if you want to be very accurate, if you want to be true to the terms, piezo-resistance sensing is about the changing the resistivity of the material. We'll see that you also get a change in dimensions, and that also affects the resistance of a piece of material. But piezo-resistive sensing, if you want to stay true to the terms, it's about the change in the resistivity of the material. Now, in many cases, the interface that we have to the real world causes a mechanical change and then produces a displacement or stress at the end of the story. One simple example is that if you want to measure the pressure, you can have a membrane here, and then if the pressure, keep the bottom of the membrane at a constant pressure. If the pressure on the top of the membrane changes, the membrane will deflect. And the deflection of the membrane, you have some displacement, let's say at the center of the membrane, that you can measure, or you can measure the stress that is produced as a result of those deflections. So through that mechanism, you can actually measure pressure if you could measure the strain at the edge of the membrane or anywhere else, as long as you just want to do a measurement, but optimum location is around the edge. An accelerometer, the way it works is that you have a mass that responds to a mass with some springs, and then if you have an acceleration, the proof mass displaces. So to measure the acceleration, you can measure that displacement of the proof mass, or you can measure the strains or stresses that are going to develop inside the springs in response to that displacement. And so if we find a way to measure that stress or strain, we can make all sorts of sensors. So in resistive sensing, and we'll talk more about the interfacing to resistive sensors in coming lectures, whatever you're measuring affects the resistance, right? And then in case of piezo-resistive sensing, the stress is changing the resistance. There are other types of resistive sensors that you may use. So for example, you can have thermistors. These are resistors whose value depend on the temperature. Or you can have chemoresistors. These are resistors whose value depends on the concentration of a certain chemical in the environment. Piezoresistors are devices whose value will change or will respond to an applied pressure or stress or strain, right? So piezoresistive sensing then becomes the measurement of stress or strain, mechanical stress or strain, through measurement of the resistor, whose value depends on stress or strain. So if we go back, you can recall from basic electrical engineering or electric circuit courses that the resistance of a simple resistor with a constant cross-section and a length L, and typically the assumption here is that it's a long resistor with then the resistance of that piece of material, that resistor, is given by the expression shown here. Rho is the resistivity of the material, L is the length of the resistor, and A is the cross-section, which is assumed to be constant throughout the length of the resistor. And if you have that and you want to see what happens if you have a change in any of these parameters, you can show that. Actually, let me maybe quickly try to drive that equation. So rho L over A. This is what we know from before, right? And then if your resistance changes for whatever reason, let's say something affects rho, something affects L, and something affects A, we can show that the change in resistance is a combination of all of these. So you take the relative differences and multiply it by the rest of the parameters as constant. So you're going to have some change in delta rho, and the rest is a constant, and then some change in L times the rest, and then some change in A, but A, because it is in the denominator, your delta A appears as this. Okay? And now if I normalize this by R, I will get this relationship. So the first term becomes delta rho over rho, the second term becomes delta L over L, and the third term becomes delta A over A. Okay? And now noticing that, because if I go and look at the case where the change in resistance is because of a strain, I have applied the strain to this resistor. So this is the resistor that I thought I start with. So I have some cross-section. The cross-section could be anything as long as it is constant along the length of this resistor, and this is the area A, and I'm measuring the resistance from these two ends of this device. So in this case, R is given by that expression here, right? So now the issue is that I have applied the strain to this. So let's say a stress or force or pressure has changed the length of this material by some value, and the material is responding to that. So those changes that I have in that relationship, delta rho over rho, delta L over L, delta A over A, they are because of the stress and or strain. And because of that, now I can simplify this. I can say delta L over L, well, this is already epsilon. This is a strain. I know that. Delta A over A, if you assume the Poisson's ratio is the same in, let's assume this is an isotropic material, you can show that this is going to be proportional to delta A over A is going to be proportional to minus 2 nu. And the reason for the negative sign is that, when you make it longer, when L becomes longer, the cross-section reduces, right? So you can show that, it's just an approximation. You ignore the higher order terms here. You can show that delta A over A will be proportional to minus 2 nu. And now going back to this is the end result. So delta R over R, if you apply a strain epsilon to this structure, it's going to be given by that expression. So there's going to be a term delta rho over rho, and there's going to be a term that is because of, so delta rho over rho is a property of the material that has changed, right? So rho, remember, is resistivity. Delta rho over rho is the change in the resistivity of the material because of strain. And then there's a second term, epsilon times 1 plus 2 nu. That second term is geometrical, right? So that term, you have that change in resistance because the geometry of your device has changed, your resistor has changed. It is now a little bit longer, a little bit, let's say, has a smaller cross-section, and for that reason, the resistance definitely will change. You have these two issues, phenomena that happen at the same time, parallel with each other, and what happens is that we can normalize this to strain. So what we do is that we go and normalize delta R over R, you know, that normalized change in resistance, we normalize it again to strain. And we define a gauge factor as shown here. So gauge factor is the change in resistance normalized with its initial value divided by strain. You can think about it as the sensitivity of the normalized resistance to strain. Now, what happens next is that for metals, normally in most situations, the electrical resistivity doesn't change that much. These are such good conductors that, you know, even though delta rho may change a tiny bit, it's just negligible compared to the geometrical effect. So the second term, that epsilon times 1 plus 2 nu, will dominate. And when you normalize it by epsilon for gauge factor, you have 1 plus 2 nu as delta R over R value. Nu is typically somewhere between 0.2 to 0.3, 0.4. So the gauge factor for metallic strain gauges is about 2, because you don't get a contribution from the first term, very small one, and the second term, you know, the most you can get is about 2 for these metallic gauge factors. Strain gauges, we call them, right? And these are used all over the place. So you can just do a quick search on the internet, strain gauge, and what you will find out is that there are usually platinum-based strain gauges that you use for measuring strain in a certain direction with these devices. For semiconductors, on the other hand, the situation is reversed. We still get the geometrical effect, but the change in the resistivity of the material is so large that the second term, the 1 plus 2 nu part, is negligible. You can get gauge factors as high as 100 or more from these semiconductor devices. For silicon, you can get gauge factors of more than 100 easily if it is single crystalline silicon. Of course, it depends on doping and dopant concentration and all those issues that we discussed before, and I'll show that to you in upcoming slides. But it's a very sensitive method to measure strain. You get huge gauge factors, and if you don't have access to single crystalline silicon and you want to use polysilicon, that's fine. With polysilicon, you still get gauge factors on the order of tens or maybe 20 or 30 or so. So still much higher than what you would get with a metallic strain gauge. So for that reason, actually, piezo-resistive devices, and this is a property of silicon which was there from the beginning, it is your fundamental structural material. Piezo-resistive devices have been around since the beginning of the micromachining, let's say, technologies, the development of these technologies. So let's have a quick look at an example here. So what I do is I have a cantilever. Let me see if I can get my pointer up. So this is the side view for the cantilever. I'm pushing the tip of this cantilever down, and because of that displacement I have here, I will develop stress at the bottom, well, all along the length of this cantilever other than the neutral axis. If the cantilever is pushed downwards, I will get some tensile stress here. you can go and show that the maximum amount of stress happens at the anchor, where the cantilever meets its base. But anyway, so that's where I'm going to put my piezoresistor. This is where I will have the largest amount of stress, and I will put my piezoresistor here. This is how I put it. I have to have a path to return the current. I cannot just have one resistor like that. So usually the piezoresistors look like a U, right? So that the current goes into this resistor and comes back. I need to pass the current through this device and measure the changes in current with a constant voltage, or measure the changes in voltage with a constant current. But I need to provide a path for the current. And now if the tip of the cantilever is pushed down, I will have some stress here. My piezoresistor will respond to it, and I will be able to measure the change in that resistance as a function of the force. The question says that, we have a gauge factor GF for the piezoresistor, and what we want to find out is the sensitivity of the device in terms of the relative change in resistance to a point force applied to the tip of this cantilever. And these are the parameters for the device. So we have a length of L, width of B, thickness of H, and Young's modulus of E for this cantilever and its material. So what I can do here is go and solve the deflection equations that I had. I have the boundary conditions. It's a cantilever, point force at the end. I can go and solve them. And basically, figure out the stress as a function of force. So if we go back into the material that we learned earlier, I can go and solve the differential equations and then derive the deflection equation, or I can just go and look it up from one of those tables that we had. So we had psi of x for a cantilever with a point load at the end. You can go and look it up from the tables that you have in your text, in your slides. It's going to be minus f over 6 EI times and this is the device. So this is my cantilever, and let's just assume this end is fixed, right? This is L. I have a width of B and a thickness of H for this device. Now, because I'm pushing it downwards, I can go and show that I for this device is going to be the moment of inertia that I need here is going to be B H cubed over 12. Okay? So remember, in whatever plane that you're bending the beam, you have to take the thickness in that plane cubed times B divided by 12. So knowing all that, I can then see that psi of x is minus f x squared divided by, so I will have a 2 up here, E times BH cubed times x minus 3L. Okay, so this is the deflection equation. But what about the stress at where my piezoresistor is? So in this case, the piezoresistor is going, the piezoresistor is going to be close to this space right here. Okay, so I'm going to assume the piezoresistor is small compared to the length of the cantilever, so I'm just going to focus on the stress over here. Then again, if I go back to the discussions we had regarding the beams, I can recall that the strain at any distance y from the neutral axis was given by this expression, y over rho, the radius of curvature. And then I again remember that 1 over rho was the second derivative of the deflection equation with respect to x. Okay? So these are the information we have from the past. Then what I'm interested in is the stress at the top, or the strain at the top of the beam. So the first thing I do is I go and calculate the second derivative of psi of x, or psi prime of x. The first derivative is going to be minus 2f, let's just write it like this, e bh cubed times 3x squared minus 6xl. And then therefore the second derivative of psi is going to be minus 2f divided by EBH cubed times 6x minus 6L. Okay? And so that's the second derivative. And I want epsilon at the top of the beam. So y in that equation that I have is going to be h over 2. Because this is a beam of a rectangular cross-section, the neutral axis will lie in the middle of the beam. So y is the distance from the neutral axis. At the surface, it's going to be h over 2. So therefore, I can show that E epsilon at the surface, or y equal h over 2, is going to be, so h over 2 times the 1 over rho, which is the second derivative of this device, the second derivative of the deflection equation. So it's just going to be, I bring out 6 from that bracket, so it's going to be minus 12f over EBH cubed times x minus L. Okay? Now, it's a simple equation here. You can easily see where I will have the largest strain. So if you look at x, x is measured from here, right? The origin is on the anchor of the cantilever. And if that's the case, you will see here easily from this equation that the maximum strain you can have is when x is 0. Because if x is larger than 0, and as it goes towards L, you get a smaller and smaller value for x minus L. You can do the same thing, just by going and taking the derivative of this and showing that. But anyway, at x equals 0, you will have the largest strain. And linearly, the strain at the surface drops all the way to the tip of the cantilever. So if you want to put a piezo resistor somewhere, you want to put it where the strain is maximum, and for that reason, you would like to put it as closely as you can to the base of the cantilever. So epsilon max then is going to be at y equal h over 2 or minus h over 2. Bottom of the cantilever will give you the same amount of strain, but it will be compressive, right? And x will be 0. So if you plug it into that equation we have at the top, it's going to be, and I'm going to simplify this a bit, so it's going to be 6f over EBH squared. One of the h's cancels. And x is 0. I have negative L over there. It just comes out, right? And cancels the negative in front of the equation I had. Okay, or let me just write it as a constant times the input force. Okay? So now you have a value that gives you the strain at the base of the cantilever, or an equation that gives you the strain at the base of the cantilever based on how much force you apply to the tip of this cantilever. And we have a piezo resistor there, so what you can say is that delta R is the gauge factor times, so remember gauge factor is delta, let me just go back to the definition here. So remember gauge factor was defined as delta R over R normalized by strain, or the sensitivity of delta R over R to strain. And with that in mind, I know the gauge factor for this cantilever in this problem. I can go and show that delta R therefore is my gauge factor times epsilon times the initial value of the resistance. Okay? And therefore, if I'm looking at the sensitivity of delta R to force, right, that's what the equation, the problem asked from us, I can show that this is going to be, well, gauge factor times the initial value of the resistance. That's a constant, right? And then I have an equation for epsilon. So that's going to be 6L over EBH squared. It is multiplied by F, but then you take the derivative when you're calculating the sensitivity, so F goes away. So this is the final result. The sensitivity of this device to stress is given by this expression here at the end. Okay? And right away you see some factors that affect your sensitivity. Obviously in most situations we want a high sensitivity, so a large change in resistance as you poke the end of this cantilever. So you would like to have a large gauge factor. You know, use the best material that gives you the highest gauge factor possible. The other thing you can do, if you have a choice, you can go and play with the dimensions of your cantilever, right? Sometimes you cannot do that. But if you can, you know, a longer cantilever will give you a larger strain for a given amount of force. And the reason is that a longer cantilever will be softer. So this given amount of force will deflect it more, and therefore you develop more strain at the surface here. And B, H squared, and E are also parameters that you can play with. And just go and think about it for a bit, and then convince yourselves that all of these make sense. They need to be there. So with piezoresistors, things are not really too difficult, and it's fairly easy and linear. The calculations are relatively straightforward. However, when you talk about piezoresistive or piezoresistors that are made out of semiconductors, and you already know about this, we need to worry about the direction. Remember that a lot of these semiconductive materials, they're crystalline. Once you have a crystal, everything is a function of the direction. And that's the case for piezoresistivity. Actually, if you go and look at the piezoresistive coefficients for materials, let's say silicon, it's a strong function of the direction that you have. To make our lives a bit easier, what we do is that we come and, again, similar to what we did for estimating the Young's modulus in a crystalline material, you know, instead of going through all those matrix calculations, we came up with an equivalent Young's modulus, right? Here we do the same thing. We come up with an equivalent couple of piezoresistive coefficients that make our lives easier when we deal with semiconductor piezoresistors. So let's assume that I have a piezoresistor that is much longer than it is wide, and the thickness is usually negligible compared to both of those dimensions. So for example, your thickness may be, for this piezoresistor, maybe half a micron. The width is a few microns, and the length can be tens of microns. So the thickness is usually much, much smaller than both of the other dimensions. And in this case, we're assuming that the resistor is long, or much longer than it is wide. If that's the case, when you apply an electric field across this device, the current will go from one end to another, and in almost a uniform manner, you know, and spread almost uniformly across the piezoresistor. And what we do is that we go and say, the length of this resistor, you know, whatever that length of the resistor is, we're going to take it as our longitudinal axis. And what I do is that I go and calculate how much stress is applied along the length of this resistor, and how much stress is applied normal to it in the transverse direction. And I calculate two equivalent coefficients for the change in resistance because of the stress applied to the length or parallel to the length of this resistor. And so that's pi L, longitudinal piezoresistive coefficient in the equation you see over there, times sigma L, the stress applied in parallel with the length of the material. And then there's a second term that goes and says, okay, so I may have a stress applied normally to this, in normal to the piezoresistor, basically in parallel to its width instead of the direction of the current. And if that is sigma t, then I go and assign a pi t, a transverse piezoresistive coefficient to that stress. And that gives me another component for change in resistance. So if I'm looking at the change in the resistance, delta R or delta R over R, I go and calculate it from this coefficient. So what I need to do is to know pi L and pi T for that piezoresistor, and that is direction dependent, right? So we calculate those based on the orientation of the piezoresistor, or we just stick to whatever the manufacturer tells us. So if they say that if you put your piezoresistor in this direction or that direction, these are the piezoresistive coefficients you get. So once we have that, we stick to those directions and we'll be fine, or we go and calculate them from the matrix, from a more detailed analysis if we need to. Now, if you're using a piezoresistor to measure the stress inside the larger body, which is usually the case, it could be, and this situation happens a lot in MEMS, that your piezoresistor is actually part of that body, right? It is deforming with that body. When does that happen? So we said that, piezoresistors, you can make them out of crystalline silicon. And what I can do is that I can dope a segment of that crystalline silicon. Let's say the silicon itself is N-type. I can dope it P-type and pass a current through that P region only. So I will have a diode that separates it from the rest of the structure. But from one end of that P region to the other end of that P region, I can have a piezoresistor. This resistor is embedded within the structure. Mechanically, it is going to basically follow the larger structure around it. And if you have a, let's say, longitudinal stress applied to the structure, the resistor deforms with it. You don't have any normal stresses applied to that structure. So in most of those situations, when the device is embedded, when the piezoresistor is embedded within the main structure, sigma t will be 0. You're looking at the transverse longitudinal stress only. But there are situations where the piezoresistor does not follow the deformations of the main body. So maybe for whatever reason your piezoresistor is stiffer than the main body. So the main body has deformed. Let's say you stretch it in this direction. The Poisson's ratio means that it is going to now basically stretch in the other direction or shrink in the other dimension a little bit. But your piezoresistor is a stubborn little thing and doesn't conform. In that case, you will have the longitudinal stress applied to it as well as the transverse stress, because the material underneath has shrank a bit in that direction, and then because the two are glued to each other or fixed to each other, your piezoresistor will feel a transverse stress as well. This can happen, and you can, in macro scales, you can easily do this. Micro scales, this is really not the case. In most situations, your piezoresistor is deforming with the larger body. It's following whatever the larger mechanical body is imposing on it. And therefore, sigma t is 0 for most of those situations. In the other case, sigma t will be nu sigma L, right? So remember that the piezoresistor hasn't deformed, but the material underneath has. The shrinking is about proportional to nu, right? The Poisson's ratio. So the sigma t will be nu times sigma L. And this is the variation in piezoresistive coefficients in N-type and P-type silicon. And obviously, you can see that there's a huge variation as you look at different directions. And the numbers, what kind of values we can expect for pi L and pi T for typical doping levels, they're about 50 to 100 times 10 to the minus 11 pascals. So the numbers seem small, right? So let's say 100 times 10 to the minus 11 pascals. It means that if you apply 1 megapascals of pressure to this resistor, the change in resistance is going to be 100 times 10 to the minus 5, or maybe to put it in it's 1,000 ppm, or 0.1%. So the change in resistance due to 1 megapascal of pressure is just 0.1%. It may seem small, but it turns out that it's actually a very easy to measure value. So that kind of a sensitivity is actually fairly high. And when we look at other transduction mechanisms, you see that piezoresistive sensing is usually your go-to method is available. Now, one interesting point to note here is that pi L and pi T have different signs. So pi L is negative and pi T is positive for N-type silicon. For P-type silicon, pi L is positive and pi T is negative. And if the second situation over there happens where your sigma T is nu times sigma L, this actually could give you some benefit, right? You get a contribution from the longitudinal part as well as the transverse part. But as I said, in most cases, sigma T is going to be fairly small. In silicon, as everything else, you can expect, and it is the case, that piezoresistive coefficients are dependent doping. As you increase the level of doping, the piezoresistive coefficients start to drop. So the other way to think about it is that as I'm increasing the doping level, I'm making this piece of material more and more conductive. I'm making it more and more like a metal. And therefore, you should expect a bit of reduction in sensitivity to strain, or piezoresistance on the other hand. That's okay. Once you do the fabrication and the doping levels, you can live with that. The challenge we get is that the piezoresistive coefficients are also very sensitive to temperature. And that makes life difficult. Now, if you measure a change in resistance, you really cannot distinguish between the two. You cannot tell if it was the temperature that changed the resistance or if it was an actual mechanical strain. And that uncertainty is expensive in engineering, right? So how do you deal with that? Well, maybe you go and put a temperature sensor next to this thing. So you measure the temperature and you go and correct the reading from your piezoresistor, but that means additional cost. So what people normally do is that, despite the fact that at higher doping levels your sensitivity drops, but if you look at these two curves, your sensitivity to strain drops, but your sensitivity to temperature also drops significantly. And that's the sacrifice that in many situations people make, right? So they trade off the sensitivity to strain and gain insensitivity to temperature by having highly doped piezoresistors. So, to sum it up, if you have a technology that lets you make piezoresistors, in that technology to measure stresses and strains, they are usually a simple and first approach type of a mechanism for strain sensing. Layout orientation is critical. If you are especially dealing with single crystalline material, there are orientations that give you maximized sensitivity to strain, and there are orientations that will be less sensitive to strain. So you want to make sure that depending on what you want to do, you're careful and you're aware of that. If you're dealing with polycrystalline, for example, silicon or other amorphous materials or things that are not sensitive to direction, then you don't really have to worry about this issue. Piezoresistivity is a function of doping and temperature. We just discussed that. Piezoresistors are often photosensitive, and in the brackets you should have semiconductor piezoresistors. So keep that in mind. Like temperature, it could be another interfering factor. So if you're using a semiconductor piezoresistor, be it single crystalline or polycrystalline, light may affect the value of the resistance. Because piezoresistors measure the stress along their length, you want to place them where you think you have the maximum level of stress in that structure. So for example, in the cantilever problem we just talked about, I put it at the top surface or bottom surface. I do not try to embed it, inside that cantilever. Although it's even more difficult to embed it inside that cantilever, but for let's say sensitivity reasons, the top and bottom surfaces are the best places to place your piezoresistor. Usually you don't have access to the bottom surface, so it's the top surface that you use. But where on that structure, usually, again, you can find other places with the larger strain values, especially if the deflections are more complex than what you get from a cantilever. But usually close to the anchors, close to the bases of these structures is where you have the largest stresses. It's a fairly linear measurement technique. Up to about 100 megapascals for silicon is fairly linear, so you don't really have to worry about nonlinearities. However, and we'll talk about noise a little bit later, resistors produce noise, and therefore piezoresistors, which are a type of resistor, will produce noise. And that noise puts a limit on the smallest strains that you can measure. Right? So if you're producing such and such amount of voltage because of noise of the device, you cannot measure any changes smaller than that reliably. One of the challenges or shortcomings or issues with piezoresistors is that you need to have DC power consumption in order to measure the value. You're measuring a resistor value, you have to send some current through it in order to produce a measurable voltage that you can measure. Or you apply voltage and you measure current, but that means power consumption. That's what a resistor does. It's it's an element that consumes energy or wastes energy. So for very low power applications, maybe piezoresistive devices in some cases be too power hungry. Now, one other issue to keep in mind when you're using piezoresistors is that you can self-heat them, right? So you pass a current to a resistor. We know from the past that the power on a resistor is VI, right? So the power wasted on a resistor or the heat generated by a resistor is VI. So you pass a current to this resistor, you have to do it, it's a piezoresistor, you want to measure the voltage across it, and that current will heat it up. Now the problem is that your piezoresistors are almost always temperature sensitive too. So by heating it up, you change the resistance. And you have to take that into account. You definitely do not want to heat up the resistor. You don't want to make it so hot that it measurably changes the resistance. What that means is that you have to use small currents in order to measure that resistor. But here comes up new challenges. If you use a small current, well, a small current times the resistance means a small voltage. Your signals will be weaker. And there has to be a balance somewhere, right? So you go and look at your device and, maybe ensure that the heat is dissipated very well from your device so that it doesn't heat up with a slightly larger current, or come up with techniques that are not, basically take the self-heating into account. Now, here are some structural examples for how you can use piezoresistors. So the top one, we already had a look at it. This is the side view for a cantilever. You can put your piezoresistor like this. And in this case, you are basically using the pi L of this piezoresistor. Or you can put it like this. And in this case, you're using pi T of the resistor. Remember that when you apply a pressure to the tip or a force to the tip of this cantilever, it bends down. You have a stress in this direction along the length of the cantilever, and it's normal to this fellow here, but parallel to this one here. So depending on how you orient your piezoresistor, you can take advantage of pi L or pi T. If you have a membrane as shown below, you can have piezoresistors close to the edge of that membrane. So again, this is one that will give you a longitudinal stress here, but for this guy it's going to be a transverse stress. And these are the typical geometries for applying piezoresistors to a structure. In many cases, a transverse piezoresistor, this guy, can give you higher sensitivity because the device is narrower. You can put it such that the entire width of that piezoresistor experiences the maximum stress as you push down, let's say, at the tip of that cantilever. For the transverse ones right above it, let's say left end of that cantilever is seeing the maximum stress, but we just solved the problem. You see the stress drops linearly with X. So if it is a long resistor and then you have to loop it back, let's say first 10% of it see a lot of stress, but the stress starts to drop. And you get less than ideal or less than maximum stress levels along the rest of the device. So the delta R over R value may be smaller. That's true in most cases, right? So a transverse device like this will give you a higher sensitivity. However, this device here is more susceptible to alignment issues. So like the case shown here, you may go and be conservative and just put it slightly into the device so that you are sure that it is experiencing some bending. But if for some alignment issues your piezoresistor just happens to be on the solid part, on the base part, it will not see any stress. So you lose all of your signal. However, the longitudinal one here, if there's a little bit of misalignment and you put some of it further down here or a little bit further towards the center, it still gives you a measurable signal. It still can function as a piezoresistor, maybe suboptimum, no, but it still gives you a signal. The transverse one can actually lose all of the signal if it just happens to fall on the solid part. So, we like them both, but usually if you're sure of your process, you want to use the transverse one. If not, use the longitudinal one. But also keep in mind that, the pi L and pi T were, for, let's say, silicon, they were large values, but they had opposite signs. And therefore, for example, if you assume pi L is positive here and pi T is negative here, this resistor value decreases, this resistor value increases with the same pressure applied to this membrane. Or if you look at this cantilever, let's say pi L is positive and pi T is negative. So the resistor here will have a larger value if you push this down, and this will have a smaller value compared to the rest position. So you have one resistor whose value goes up, one resistor whose value goes down. That actually is a very useful feature. You can use it in differential sensing that we will talk about later on. And now here is an example of an actual MEMS device. This is a pressure sensor, and as you can see, they're doing what we had on the previous slide. So there's this longitudinal piezoresistor here, the transverse one here. They put 4 of them in a formation called the Wheatstone bridge. We'll talk about it later. And that gives you a little bit of dependence from temperature. It gives you a differential signal. It gets rid of some of the other parasitics that you may have as well. Now, here is another example. In this case, coming back to what we solved before, we have an accelerometer, right? So if you go back to the previous example, we had a cantilever when you apply the force to it. In this case, we are not applying a force. In this case, we have a proof mass at the tip of the cantilever, and the force is the inertial force due to the acceleration that is applied to the device. So it's a piezoresistive device, piezoresistive accelerometer, and what you want to find out is that Well, if you have two configurations of piezoresistors, one longitudinal and one transverse, what are the sensitivities that we get? And how can we produce a circuit or have a circuit to get a maximum signal out of this device? And device parameters are given as shown here. So the assumption here is that the piezoresistors follow the deflections of the main structure, or let's say, in other words, they bend with the main structure, right? So basically, you can have only one component of structure. So this is the structure we want to analyze. So I have the proof mass here, so some m naught. I'm going to ignore the mass of the cantilever for this problem. So the thickness is h, and it's of course a 3D structure, so let's say this width is b, I think, and the length is l, right? And the acceleration is applied here. We already solved a similar problem. We know that the response to a force, well, the force in this case is the mass that I have at the end times a, right? So ignoring the mass of the cantilever, that's the force. So what I do is that I go and use the material that I had from the previous section or previous problem and solve this. So I go back and see that epsilon max at this location, right? So over here, this is epsilon, is 6FL over BH. Okay? And if I want to find sigma, so this is the sigma in this direction, right? Again, parallel to the surface as I push down the tip of the cantilever. Then sigma that I have is, so this is sigma max because it is at the surface and at the base of the cantilever. I just multiply that by E. So it's going to be 6L over BH squared. And F is M naught A, so there is some M naught here that I can calculate from the dimensions of the proof mass and the density of the material. And A is the acceleration applied to this device. So that's the stress at the base. And then I have two resistors. So let me just draw the top view. So I have this piezoresistor, and which is narrow here. And I have a connector here. So this is the direction of stress. And I have this piezoresistor that I have placed here. So let's call this R1, or let's just call it R1 and R2. So for R1, I can see that delta R1 over R1 is pi L sigma L. I go back to the equations that I had on the previous page, pi T sigma T, right? And sigma is sigma max in this direction. I don't have sigma T, right? I'm assuming that the device is deflecting with the main substrate. It could be a part of it. So for this situation, I don't have sigma T. Sigma T is 0. Sigma L is sigma max. So this is just pi L sigma max, which I have from here. And for R2, I can see a similar thing. So delta R2 over R2 is again pi L sigma L plus pi T sigma T. But notice that these are relative to that resistor. So sigma L for R2 is in this direction. So for R1, sigma L is in this direction, and sigma T is in this direction. For R2, sigma L is in that direction, and sigma T is normal to it, right? So in this case, if I look at this resistor, sigma L is going to be 0 for the same reason that we talked about, and I only have sigma T, and therefore the output is going to be pi T sigma max. Sigma T in this case is just sigma max. And all that is remaining is to go and find values. I have sigma max value from here, and pi L value and pi T values are given. I unfortunately don't have the final answers here. But anyway, you can calculate M from the dimensions of the proof mass and density of the material that is given. And pi L and pi T are also given, and sigma max you can calculate it from dimensions of the cantilever and the value of the proof mass, and normalize it by A to get sensitivity. Okay? And I will calculate these numbers and provide them to you during the live lectures if you want to check the final values for me, with me. Now the second part of the question, at the end of the story, what you will see is that because pi T is less than 0, this sensitivity delta R over R will be less than 0, and delta R1 over R1 will be larger than 0. So R2 will reduce with pressure or same acceleration, R1 will increase. Delta R2 over R2 is less than 0. And the question says, how can we make a circuit to maximize the signal? Well, here is one possible solution. So let's say if this is R1 and this is R2, you can apply your source here. You can apply a constant voltage source or a current source and measure the other parameter. But if you put these resistors in series like this, because R1 goes up and R2 goes down, this gives you the maximum sensitivity. This circuit gives you the maximum sensitivity. We'll come back to the circuits for measuring resistive or for interfacing with resistive devices in the future lectures. But I'm hoping this is intuitive enough that doesn't need more explanation, but I will be available during the live lectures to discuss this further as needed. That's that for piezoresistive sensing. We come back to this during the interfacing discussion, but for now and for what is needed for, let's say, the assignments and the quiz on this topic, this is all that is needed in this lecture. Thank you.